This talk is about predicting gasoline shortage during disasters using social media. The outline of the talk is I'll have a motivation, then we'll have the objectives and challenges, then data description, methodology, case study and results, contribution, and then finally, future work. The motivation is as follows. Gasoline, as we all know, is an extremely essential commodity, which is useful during natural disasters because it's used for evacuations. It's also used to run generators. Those are the two principal uses. There's a surge in demand as people panic buy and they hoard up supplies. They often buy things that they don't necessarily need. And there are also shortages because people get stuck and they don't have these supplies. And these type of events have become very quite common in hurricanes. Some recent hurricanes, Hurricane Sandy and Hurricane Irma, are good examples of this. According to the Florida Department of Transportation, during Hurricane Irma, the demand went up by 150%. There was enough demand in the ports to replenish stations and satisfy demands, but unfortunately there weren't enough drivers for the vehicles, and they were later brought in from Arizona. The focus of our work is on tweeting and how can we use tweet data. And so people did tweet about these shortages, and you can see that the tweets are of different types. For example, one says the shelters are full, there is no gas. So the task is to take these tweets and kind of mine them and figure out from the tweets which ones relate to gasoline shortage. So the objectives are one, can social media data, especially Twitter, be used to predict these shortages? And if so, what type of method should be used? So this is the objective which we use to answer these questions. If the demand surges and shortages can be forecast, then the authorities could plan to respond to the demand. There's an appropriate amount of gasoline can be directed to shortage affected areas easily. So that's kind of what we're trying to achieve. So the challenges are Twitter data is difficult to process and classify. It is unstructured, it's noisy, and contains all kinds of information which may not be relevant to what we're looking for. Also, tweet has a maximum of 140 characters. It's usually informal. It contains abbreviations and spelling mistakes. And so all these things are quite common. So we need to classify tweets for a specific problem, like identifying gasoline shortage, and has never been done before. And we want to identify important features of this classification task. Our second challenge was how to forecast the actual spatial temporal shortage from tweets. So how do we actually do that? So there are two technical issues. The spatial temporal distribution of tweets are not equivalent to the spatial temporal shortage distribution. Okay, so that could be one issue. And the spatial and temporal lag between the origin of the shortage and the tweet about shortage is an uncertain quantity because a person may not tweet exactly when at the point where the shortage was. Maybe they tweet a little bit later, and we don't know. There could be a time lag. There could also be the tweet in a different place. So these are some issues. So the number of tweets is. So here's some data description, which is basically constitute the ground truth. We collected ground truth about gas shortages in Florida from 6 to 15 of September from an app called Gas Buddy. And this was done to validate a methodology. And we also collected details and predictions of the hurricane path from the National Hurricane Center website. So the methodology we used was we took the tweets from the affected area and then we applied a stage one, which was tweet filtering. We filtered the tweets using keywords. We removed stop words, spaces, stem words, etc. After stage one, we got the tweets about the commodity, which is gasoline. Then we put in a tweet classifier. We had latent topics, unigrams, SVM, And then from this, we collected tweets about commodity shortage. So now it's not just gas, it's about gas shortage. Then went to stage three, which was predicting future tweets that might be about gas shortage, which basically was worked on the premise of the tweets being through some type of Poisson process and then predicting the future tweets. And then this gives us a number of tweets in a city for the next day. And then we use this for predicting commodity shortage using Poisson regression. And this gives us finally what we need is a number of gas stations out of gas the next day. For tweet filtering for stage one, gasoline related, the filtering are filtered out during the huge corpus of tweets. We use keywords, and then we use regular expression with the grep package in R for the keyword search. We did a hashtag search, we did a tweet search, and then finally we got the results from the tweet and hashtag search. The tweets are cleaned and removed for noise and uniformity. And these are the keywords that we used, which were gasoline, gas in Miami, gas price fixing, gas station, gas service, gas state parks, gas shortage, gas oil, gas station, gas waste, no gas, out of gas, find gas. So from 1 million, we got down to 4,070 gasoline related tweets. In stage two, which was the tweet classification, we classified gasoline related into either gasoline shortage tweets or non-gasoline shortage tweets. And we used an SVM classifier with two kinds of features. There's the unigrams of words, and the latent topics were identified using 4 topic modeling techniques, which were correlated topic models, latent dialectic allocation, which is LDA, using the variational expectation minimization algorithm, and then we had LDA with fixed VEM and LDA with Gibbs sampling. To find the best number of features, we conduct an experiment. We fix the number of latent topics in the model and varied frequency thresholds of unigrams, and then finally we fix the number of unigrams and vary the number of unigrams in the models. So this is how we got the number of topics. So the best F1 score was using 5 unigrams and 5 topics. The 5 best unigrams of gas get line out at station, and the 5 topics were as follows. In topic 1, it was gas. The words were gas, cannot, find, know, and where. So these are the different topics, the 5 topics, and then 5 unigrams for each of those topics. Then this brought us to stage 3. We are predicting the number of future gasoline shortage tweets. So to forecast the spatio-temporal distribution, we did that, and you can see on these figures, we basically forecasted the heat. They have a heat map of gasoline shortage tweets starting from September 6th going on to September 9th. And then we also have city-wise geolocation of gasoline shortage tweets for Tampa, Miami, Jacksonville, and Orlando. And they fit a Poisson distribution. So in stage 3, the arrival of gasoline shortage tweets followed a Poisson distribution. The candidate methods for tweet forecasts were ARIMA, SARIMA models for time series modeling, and the Poisson regression method. We tried both, and to increase the accuracy, came up with a hybrid loss function which combines ARIMA and Poisson regression methods. So here's our hybrid loss function, which is convex, and for which we have the following gradients. And then we did the prediction. We're predicting the number of future gasoline shortage tweets. We were able to do that, and so we have p-values. This is the results of the p-values and the z-values associated with this, which we're talking about the gas shortage one that day, number of gas stations on the hurricane path, etc. And this is ARIMA modeling for the city of Miami. You can see this in the time series modeling, and we can see the tweets, the time, given us the number of tweets with time. And then we use this for predicting the number of future gasoline shortage tweets. And we predicted, so that we had the number of tweets, we predicted using time series, using Poisson regression, using the HLF method for the cities of Tampa, Jacksonville, Tallahassee, and Orlando. Then we were predicting the number of future gasoline shortage tweets. And again, we're continuing that. We have Gainesville and Miami, and then we have the MAPE score and the RMSE scores for these. Finally, our methodology in stage 4 is predicting the number of stations without gasoline. It's a Poisson regression model, and for IRMA data, it fits the data extremely well. And this gives us the number of gas stations without gasoline, a prediction. So here's our contribution. Our aim was to build a classifier that identifies gasoline shortage tweets from a corpus of all tweets generated for an event. Our second contribution was discovering that the arrival of tweets about gasoline shortage follows a Poisson distribution. Our third contribution was developing a hybrid loss function method that forecasts the number of tweets about gasoline shortage. And then we had the development of a 4-stage gasoline shortage prediction methodology that takes tweets generated in a day and an affected city's input, and then generates the most important thing we need is the number of stations that will be out of gas the next day as the output. That's the output we need in order to figure out where we need to supply gas. Model validation was done with a case study based on Hurricane Irma. For future work, the F1 score for tweet classification is good, but recall it's relatively low compared to the precision, so that's not necessarily a good thing. Reduction of false positives in the future, we suggest that using other techniques like recurrent neural nets. Second future work is our method does a coarse grain prediction of gasoline shortage, predicting the number of stations without gas in a city, because we really actually didn't have ground truth about individual gas stations from GasBuddy. In the future, we would like prediction at individual gas levels if the ground truth is available. This would be much more useful from a consumer perspective if we knew which gas stations were likely not to have gas or not have gas. Also, in future work, we want future shortage data is available if it's available at the individual gas level, it can be fed into a decision-making model for gasoline delivery to gas stations to ensure adequate supply where it is needed. So using the analysis from the tweet into a decision-making model to decide how to deliver gas, that's the ultimate aim of our work. And of course, this type of delivery model would be a vehicle routing type of formulation, which would be running off social media data. So that's a pretty interesting aspect, we believe. Thank you very much, and I hope we enjoyed the presentation.